So dealing with gauge symmetry is there are various. There's kind of a long story about possible ways of doing it, but you have to, in some sense, you have to do something about this in order to apply the kind of standard quantization methods that we want to use. So the first method would be so one is go to find a physical gauge. And the idea of a physical gauge is that you impose some extra conditions on the some kind of extra conditions which remove your ability to make gauge transformations. They you know what was a freedom of adding this of changing A by a gauge transformation will take you out of the gauge. The so-called gauge fixes it. And so, and the main example, so we know that is something called Coulomb gauge. And so then what you have is your phase space is really going to be, it's going to be given by pairs of data, which are, okay, so, and maybe I should say what Coulomb gauge, you've done two things. One, you've set A0 is equal to 0, and then the other is you're gonna do impose a condition like this. So what this means in some sense is you've got your coordinate like degrees of freedom are these vector fields for each x at time 0, and then the corresponding momenta are minus the electric field. These are just really the dAdts. But then the problem with this is that there's still you can still do gauge transformations on this, and if you want to so we have to impose this extra condition, the Coulomb gauge condition, such that plus the condition okay. And so so what makes this kind of difficult is that or a little bit tricky, not that tricky, is that what you're dealing with is everything is behaving just kind of as if you had three copies of the Klein-Gordon case, but then you've got some extra condition, which is cutting down your phase space, this phase space to this phase space plus this condition. So instead of having 3 degrees of freedom at each space-time point, this is gonna cut it down to 2 degrees of freedom at each space-time point. And these 2 degrees of freedom are going to correspond to the two different polarizations of the photon. And I think I don't know if I want to say more about that, but anyway, okay, let me not go through what I did then last time, but basically what's happening is it's the easiest to see what happens in momentum space. In momentum space, you have a momentum vector, and what you want to do is the Fourier transform of this guy has to be so-called transverse. He has to be orthogonal to this guy, so he has to live in the orthogonal two-dimensional space. And what you do is you basically choose as a function of p, you decide to kind of parameterize this two-dimensional space by choosing vectors, epsilon1 vector, a p vector, and epsilon2 vector, a p vector. So you make some choice of a orthonormal frame, and there's a thing we discussed a bit last time about the problems of not being able to continue it to necessarily do that continuously, but you do. Anyway, you do this, and then what you find is that you can parameterize these solutions that obey this condition as in terms of kind of 2 degrees of freedom, one function of p that multiplies this guy, and another function of p that multiplies this guy, and those give you your so instead of having 3 degrees of freedom at each point, you've got just linear combinations of these two vectors. Okay. So that's the physical gauge. Then that's this one. Now the trickier thing. So the problem with this is this is not Lorentz invariant. So by doing both of these conditions break Lorentz invariance, and your Lorentz transformations take you out of this gauge. And so if you're trying to understand what Lorentz transformations are going to do to this theory, whenever you do a Lorentz transformation, you have to also do a gauge transformation, and it becomes very tricky to figure out what's going on. So then you want to do what I call so the next idea is a covariant gauge. And then let's see what I wanted to do. And so the so here the standard example, the simplest example of this. There are many other things you can do of this kind, but the standard example is called Lorentz gauge. Again, no T, Lorentz gauge. And this is going to be, so now what you want to do is you want to take, okay, so the idea is to quantize, well, consider your a mu of p x vector that satisfying the massless wave equation, and B the Lorentz gauge condition, which is minus dA0 dt plus rad a vector. Okay. And so this has these. So and this condition is Lorentz invariant. And if you take a Lorentz transformation on A, and you'll preserve this condition. Okay. And then what you show is that if you satisfy both of these conditions, you're also satisfying the that also gives you a solution to the Maxwell equation. So there's a bit of a calculation we had to do last time to show that. But this looks kind of nice and simple. So here looks like you just got kind of you basically got just kind of 4 copies of the Klein-Gordon story of the massless Klein-Gordon story, and then you've got this one extra condition. But there's 2 problems. And one is that the Lorentz invariant inner product on a mu is not positive. Okay. So in other words, so the problem is that you've got 4 copies of the you've got these a mu's for mu's equal to 0, 1, 2, 3. It looks like it's just 4 copies, and they're satisfying 4 copies of the Klein-Gordon equation. But the problem is that if you want to write a if you want a Lorentz invariant theory, you have to kind of create a Lorentz invariant collection of annihilation and creation operators of these guys, and you need the you need to use the Lorentz invariant inner product on these 4 vectors. which has a negative term. So remember that a mu. So you often write it in this thing. The Lorentz invariant combination is minus a0 squared plus a vector squared. So the problem is that these four indices, one behaves differently. And if you want to write down if you want to have Lorentz invariant collection of annihilation creation operators, you need a Lorentz invariant inner product. You need to use this, and you're going to get the wrong sign on the one set of the annihilation creation operators. Okay, and then then the second problem here that you had was that you had again you have the problem that this doesn't completely fix the gauge freedom. That you still can add gauge transform phi. Okay. So if you have one solution with a certain, if you have one solution to this set of problem with it, or if you like, if you go to momentum space, what this says is that you can add anyway. Lorentz transforming this, you can add extra kind of things who, if you take phi tilde of p, you can add anyway. You can add phi tildes of p, which are functions living on the light cone, so that this guy gives you 0. And if you take any a mu tilde of p and add a p times a phi tilde of p, then you'll get that corresponds to gauge transformation, and that will still satisfy both this equation and the massless wave equation. So the problem is that this is not a so these conditions are not a physical gauge. They haven't completely fixed the gauge freedom, and you've got this extra gauge freedom. So now I think what I better do then is not go deeper into this, but the claim is that in some sense you can cancel, if you do, there are various ways in which you can try to cancel these problems against each other. In the sense if you just quantize away, then problem A means that you're going to have you're going to do a Bargmann-Fock quantization, but you're going to have one of the degrees of freedom is going to be have the wrong sign, and is going to give you is going to give you negative norm states with negative norm. And then what you have to do is then say, okay, well, is somehow use this extra gauge freedom to kind of impose a condition on the states that they be gauge invariant, and that condition of them being gauge invariant removes the negative norm states and gives you a. But the way this works out is a bit tricky, and I put some more details in the notes, and this is worked out in, anyway, some version of this is in quite a few quantum field theory textbooks. Okay, so this is the main part of the story. Maybe I'm going to let me say one thing about another kind of philosophy of this, because it's maybe a little bit conceptually interesting, though not actually. These are both kind of calculationally useful. But maybe the other thing to say, the other reason for being interested in this problem is that if you try and do this for Yang-Mills theory, you find in all these cases you run into one technical problem or another. So what I've told you works nicely for a free field theory, of photons. But if you try to deal with Yang-Mills theory, where the analogs of the photons are interacting with each other, and they're not, some of these equations, like this one and this one become nonlinear equations, and they don't have this nice kind of set. There isn't kind of a nice way to write down their solutions in ways that you want. yeah. So let me just quickly tell you, because it's maybe a good idea to think about conceptually. Is a third possibility. Is a three, and this is what. So there's another thing we could have done with time-like gauge. Let's see. Yeah. So you could have if you just do this, so you just do this. So what you've done is you haven't completely fixed the gauge. So you have a problem. And this is sometimes called time-like gauge. You have a problem. Again, in some sense, again, you have two problems. One is that you don't. You can still do independent gauge transformations. And so time-independent gauge transformations will preserve this condition, but they'll have the same problem, that they'll take they'll take a solution which you thought was the unique solution with that initial data. They'll take to another one. Anyways, but in some sense you still have this problem. This is a problem that we got rid of it in the using the Coulomb gauge. But instead of using the Coulomb gauge, okay. Anyway, the other problem here is that you don't have you don't have Gauss's law. So you have one of the if you look at what's going on here, you find that there's nothing in the setup that that's going to enforce this condition. So you have remember there are two non-trivial kind of equations of motion for this theory, and so you have one of them, but not this one. And so in some sense, what you've done is that if you try and quantize this theory, actually maybe the thing to say about it is that this theory is the problem's a little bit different, because you actually do have a you do have a good initial value condition. And if you fix the initial values at a certain time, then there will be a unique solution later. Okay, so I think maybe so the fact that the gauge transformations are time independent means you don't have this problem that you can do gauge transformations at different times and change and create different solutions with the same initial data. So here you've got good initial data in some sense, but I guess I think the thing to say that's really wrong with the time-like gauge is this condition, that there's nothing in this theory that says in some sense it's because the Euler-Lagrange equation that you would like to use in order to derive this equation of motion, it involves varying with respect to A0, but A0 is 0, so you can't do that. So you can't get there's an equation of motion missing. Okay, so what do you do? So the idea is that is that in some sense this theory has too many states. Lots with So remember also that Gauss's law often was that that the if you had some kind of charge density, that the you would we're trying to do this in the vacuum, but if you actually had a charge density, then you would have this equation. So if our problem is that we don't have this operator equation, but we do have, then what's happening is that there are many states which are eigenvalues of this operator, but with non-zero eigenvalues. And those eigenvalues you could interpret as being some kind of background electric background charge distribution. So you've kind of created a you quantize a theory, but it's much too big. It has a state space which has it has states with arbitrary background electric field background charge densities. So what you want to do is so the idea is to impose a condition. So condition on states. So that, and then you say that, and then you're going to get a physical subspace of your state space, and that psi is an element of H physical corresponds to del So what we're going to do is impose this as a condition on here, and then just look at states in here. Look at states that satisfy this condition, and that's going to be your physical states subspace. And there are some. Anyway, there's a nice kind of story about trying to do that, which I won't kind of go through the details of. There's more in the book, but the thing you can notice is that del E vector is the moment map for the infinite dimension group of time in the H rotation. So what you've done, so some of the details of this are kind of worked out, but in some sense, what you've got is that you have your M is so M is equal to the set of these A of X vector minus it's this guy, but we don't have the Coulomb condition, but we do have that an infinite dimensional with a G is equal to an infinite dimensional acting. And it's just the group of gauge transformations. So this group is given by the Lie algebra of this group is just a real valued function everywhere in X. And so then you can see this is just your Q and this is just your P. You can write down the Poisson brackets on this thing. You can figure out what the knowing how the gauge transformations act on these guys, so they leave this alone, and that they add a gradient of a function phi to this thing. Then what you then you can figure out, okay, I've got an example of a nice phase space with a Hamiltonian Lie group action, and I can figure out what's the moment map for that. And the moment map for that is in a sense, which the details are worked out there, is really just this. Okay, so what you're doing So anyway, so what you're doing is, in some sense, imposing the condition that the the quantization of the function which gives you the moment map is going to be imposed as an equation restricting the states to a physical state space, and that's what you're going to do. Okay, so I don't want to. I mean, one reason we're not working out more details of this is that this way of doing things, is conceptually interesting, but it also leads to some other technical problems. And to see what the technical problems are, it's maybe a good idea to start with a much simpler example. And so I wanted to quickly tell you about that. Okay, so a much simpler example. And this is an example chosen to show you to see what the kinds of what the problems are that you get into here. Is let's say that you want to look at your system. You have a system in 3D. 3D is translation invariant in one direction. In 1D, and so what you want to do is you want to write it as as a 2D system. So the idea is that that somehow you've got this the system you're working with, and you know that you're only the physics is independent of translations in one direction, and you're only interested in states which are invariant as translations in one direction. That you really want to kind of reduce this thing to a two-dimensional system. Okay, so what you can do. Okay, so this thing tells you. So, for instance, that you have your states satisfy by P3 psi. So let's say that I guess maybe the way to think about this is that I'm trying to do, just for one degree of freedom, I'm trying to do what we were going to try to do here for an infinite number of degrees of freedom. For an infinite number of degrees of freedom, we were going to try to demand that our states be invariant under infinite group of time-independent gauge transformations. But let's think about something much simpler. Let's think about a system, and we've got just kind of a one-dimensional group of transformations acting on it, just translations, and we want to pick out the invariant piece of the state space of the full 3D state space. We want to pick out the space which is invariant in two directions, invariant in one direction. So this is the thing. So the analog of imposing the Gauss's law as a condition of states would be to impose this condition. Okay, but remember that P3 is just a minus I d Q3. So we're looking at so this picks out let's see what the I want to say this. Picks out psi of Q1, Q2, Q3 that are actually equal to just psi of Q1, Q2. So we could just fix. So one thing we could do is if we were just working in terms of this kind of configuration space, we could just impose a so we could just impose just fix Q3 is equal to a constant. And to get H phys, but there's a maybe to see kind of a problem that's going to occur is that if you try and that the functions the functions that are constant in the Q3 direction are not normalizable. So anyway, so if you're working in configuration space, you could try to do this, but the main problem that you're going to have is going to be this. And if you started out that your H was all of these with a standard norm on these things, well, that norm is you're integrating over R3. Well, if you say, okay, well, I just want to pick out the invariant things in here, those things are going to be constant in one direction. They're going to go out to infinity. They're going to have infinite norm. So there's this technical problem. Anyway, and they kind of and then so you're going to face an infinite dimensional variant of that if you try and do the what I said about the how to pick out the gauge independent states. The states where the generator of gauge independent gauge transformations is 0, you're gonna have a normalizability problem, and if you try and do that, but there anyway, you can argue your way around it or try to do something like this. But maybe another way to understand what's going on is to notice this. If you so if you what you really would rather. What you really want to do H phys is the quantization of just 2 degrees of freedom of phase of M is equal to phys is equal to R4. Okay. So this is going to have the coordinates, Q1, Q2, P1, P2. So instead of taking your 6-dimensional phase space, what you really want to do, if you want to kind of properly quantize and get a and get functions that just depend on Q1 and Q2 with a standard inner product. Well, what you really want to do is you want to cut this thing down, but the problem is that what you do when you try and cut this thing down for each degree of freedom, or for each kind of one dimensional, for each one dimension in the group that you're trying to get invariance for, you have to cut the dimension here down by 2, because each degree of freedom has both a Q and a P part. And so anyway, the what you do is you take M phys, the physical space. What you do is you take the moment map equals 0 subspace. So this is going to be P3 is equal to 0. Okay. So the moment map for this guy, the moment map function is just the momentum. It's just the P3 is equal. So what you do if you've got your 6-dimensional phase space, what you do is you fix the moment map to 0, and that's. So here you're doing that classically. That's the thing which you ultimately wanted to be true quantum mechanically. you fix that classically. But then, if you do that, you've got a 5-dimensional thing. You've got a thing that it's got Q1, Q2, Q3, and then P1 and P2, and P3 is 0. And so you have to kind of mod out this 5-dimensional space by a 1-dimensional space. So mod translations in Q3. Q3. Okay. Anyway, so the what you really want to do if you want to get this physical state space and then quantize that to get where you're trying to go, you would have to you do this in 2 stages. You first find the generator of the transformations. That's this moment map, and then you set that generator equal to 0, and that corresponds to setting the corresponding momentum equal to 0. But then you have to also mod out by the by the corresponding group action on the configuration space variables. Anyway, so this is just to give you some flavor of this thing. So let me just kind of tell you a very general story. So very generally, if you have M with a symplectic G action, what you can do is define M and then this double slash G. So we're taking the quotient by the G action, but in this kind of phase-space way. There's kind of too many. There's twice as many degrees of freedom as you thought, twice as many variables as you thought. So this thing is equal to, what you do is you take the moment map. Look at where the moment map is 0. So and then divide by the action of the group on that subspace, and this will give you a new space called the symplectic quotient. Or sometimes called the reduced. Another example of what happens, actually, if you try and do this for all the translations, you say, I've got a translation variant theory, so let's get rid of the translations. That corresponds to really just going to center of mass coordinates, and that's often called going to the reduced phase space. And then you have two possibilities. Maybe so you can take if you're M, you can quantize and get state space. Then what you can do is take invariance. So this is going to be the moment map. Operators acting on psi give you 0. Or you can take the so-called symplectic quotient. Well, you got mg, and then the idea is, and then the hope is that if you then quantize, and the hope of this whole story is that this diagram commutes. That if you get rid of your symmetry first by going to the symplectic quotient, and then quantize this kind of physical invariant piece, then you'll get some theory. And the idea is it should be the same thing as if you quantize the whole thing, and you had something that's too big, and then took the subspace of this is really actually just the subspace of G invariants. That G acts by unitary transformations on the space, and it just takes the G invariants. So the idea is that if I think it might be better to think of it that this is actually intended as a constraint on whatever your method of quantization is, whatever method you've decided to quantize things. That when you have this situation and you can quantize this guy and you can quantize this guy, then the diagram should compute and you should have this. And this is what you're trying to achieve in the if you go to time-like gauge, you're trying to do this for for G is the time-independent gauge transformation, and it's and there is a anyway, and you can see from this kind of this even looking at the simplest case that there are there are going to be problems like going from here to here, just taking the invariant subspace here. You're going to get states that are not normalizable here. So anyway. Okay, so sorry, I think this is probably far more than you ever wanted to know about gauge invariance, but I just wanted to you do run into these different possibilities at various points if you're trying to deal with these kinds of theories, and it took me forever to actually understand what was going on, and so I wanted to actually get this try to at least say this clearly once. But what in some sense makes the thing interesting is that all of these different ways, all of these different things run into different kinds of technical problems when you try and do the physically interesting case of non-abelian gauge theory. And so there's these possibilities are just kind of the beginning of a long story about what you actually really have to do to make sense of some physically interesting theories. Okay, but I think better, anyway, that's more than enough here. But any questions about this stuff, about gauge invariance, before I move on to something much, hopefully a bit more straightforward? Okay, so I'll that's it. I'll stop with the gauge invariance. But the anyway, and the other thing about this is also something. This notion of taking, if you have a symplectic manifold, so there's a general. This is also an interesting notion in symplectic geometry for mathematicians. If you have an analog of a phase space, what you call a symplectic manifold, and you have a Lie group acting on it, and you can do this and create a new symplectic manifold. So this kind of relates and things. So this gives you ways of creating new symplectic manifolds, and often if you're looking at some symplectic manifold and it looks very confusing and it has some it's a complicated, confusing thing. Often often it can be written in terms of a much simpler thing, but as this kind of quotient. So there's a lot of mathematics there. Okay, so let's get to spin half. Okay, so we've done let's see. So we've done spin zero scalar fields, and we've done these massless spin one fields. But and I haven't talked. I mean, there's a separate kind of much more. There's a different theory we could talk about of the of massive spin one fields. Those are those in some sense are in a way easier because they don't have the serious problems with gauge invariance that you have in the massless case. But they do. But they have their own. Anyway, they have their own problems, and they especially have problems with renormalizability if you try and couple them and use them to get forces. So they have their own problems. But what we're going to talk about is spin half fields. And so what these are is so here what you're going to do is you're going to quantize m equal to the solutions to the Dirac equation. what we're going to do, what we're doing in some sense is, is exactly following along what we did before. We're gonna write down the Dirac equation. We're going to find its solutions, find a way of parameterizing them, and then just then just treat that space, which is just quantize it by the Bargmann-Fock method, again with this complex structure that corresponds to separating out positive and negative energy. Okay, so that's really that's in some sense all that goes on here. I mean, one thing to say is that we're going to so quantize by usual Bargmann-Fock. And then your J is equal to is the thing that's plus I on positive energy minus I and negative energy. Energy solutions. So you're gonna need the solutions of the Dirac equation and also distinguish between positive and negative energy. And then and then one last thing which I won't say much about is we're gonna do you need to do fermionic. Okay, so what you're going to start instead of thinking of this as a symplectic phase space with an antisymmetric, non-degenerate 2 form on it, you're going to think of this as a more standard kind of inner product space with a symmetric non-degenerate 2 form on it, and then you're going to quantize it. When you quantize this, you're going to get not bosonic oscillators, which have kind of arbitrarily large occupation numbers, but you're going to get for each p, you're going to get fermionic these kind of the fermionic oscillators, which have just occupation numbers 0 and 1, and you can say I think I won't go into the story, but basically what happens is if you try and do this and you use the standard bosonic quantization on it, you get various problems, including that the states that you won't get states will go down to negative energy, will go to negatively infinite energy. You won't have positive energy states. So if you want to have kind of positive energy states and you want causality to work out, you want space like the commutator of commutator to be 0 and space for space like things, then you have to do this. But in some
so you only do the fermionic quantization when you are dealing with half integer.
So so this is part of there's a more general theorem that says that there's going to be a problem if you quantize half integer, anything with half integer, like spin half, spin 3 halves, spin 5 halves. If you try and do bosonic quantization, you'll run into trouble. And if you try and do integer spin, if you try to do spin 0, spin 1. So what I did with spin 0 and spin 1, you could have said, well, why don't you why don't you do fermionic quantization on those spaces? And you would have found that if you did that, you would have had this problem with anyway, you would have something that kind of violated notions of causality or of positive energy. So, but that's just, so there's some very general theorem. There's a very general theorem which you can prove, which really, and all it really uses is the Lorentz invariance of the theory and the existence and the fact that you want your states to be positive energy. That plus Lorentz invariance plus causality, I guess that you can prove that, use that to prove that for each case you have to use fermionic quantization for half integer spins, and you have to use bosonic quantization for integer spins. The proof's a little bit tricky because you have to do kind of analytic continuation arguments and you have to kind of go in. You have to get everything a function of kind of complex momenta, and then look at analytic continuation behavior in the complex momenta. But other than but that's a general theorem. So, but I'm not gonna. I'm not going to really do anything of this. All I'm just warning you is that this is what you're going to have to do, and at some point I'll say that. But if you tried to do what I did in the previous cases, you'd run into trouble. Okay. Yeah, then that's called the spin statistics theorem. And also but that theorem is also interesting that it's special to. It really depends upon the Lorentz invariance. It's actually not true in non-relativistically. So non-relativistically, the non-relativistic quantum field theories that we wrote down, you could quantize those either using bosonic quantization or fermionic quantization. Both would work. So you can have fermionic scalars in a non-relativistic theory. It's just you can't have them in a consistent relativistic theory. Okay, so let's go to the Dirac equation. So remember, so the Dirac equation. So remember that I define these gamma matrices. So you have 4x4 or matrices. Such that in my convention, this is -1 and gamma 1. +1. And then and then these things, and then all the rest of them, if you pick any two of them, they anti-commute. So gamma, anyway. Gamma 1, gamma 2 is minus gamma 2, gamma 1, and so the anti-commutation relations of the different ones, and this for what happens if you multiply two of the same things. These are the defining relations for the Clifford algebra. So this is the generators of what I've been calling Cliff of 4, and then so the way you generally think about this, you generally think about these as being any complex, that these are allowed to be arbitrary complex matrices. So I'll say something about this condition in a minute. So these are the generators of the Clifford algebra. And there's only but we've chosen. But maybe it's a good idea to keep in mind that we really want. Actually, maybe it's better to say that for now, because maybe I should let me just say this. It's better to say this, that these are generators of the Clifford algebra of signature 3, 1 over the reals. Okay. And so these are going to sit inside Cliff of 4C, which is M of 4C. Okay. So there's going to be some. So this condition here is. So if I look at real linear combinations of these things, I get this Clifford algebra, a real linear combination generated by this. But normally when you do this, you often think of these guys as certain special kinds of complex 4x4 matrices. So it's the standard thing that's always happening in this subject, that you really have a problem which is really a real problem, and you really have a real vector space. But in order to do computations, you want to use complex numbers. So you start throwing in complex numbers and you complexify, and then you tend to forget that you've done that, and you end up working in here. And then at various points, you have to remind yourself that, oh, wait a minute, these things that I'm working with really actually satisfy some kind of reality condition, and that reality condition is what's, anyway, that you have to be careful that you haven't messed up that reality condition. Okay. Oh, okay. So now let's define. So I'll call it So I'll write it d slash, and they're very so what you do is you write this. So let me write it this way. I'm writing. gamma 3 ddx3. So this, in some sense, is the four-dimensional generalization of what I did with when I was talking about the Pauli-Schrödinger equation. Remember, I talked about this Pauli operator, which was this guy, but where these guys were Pauli matrices. Now, and that was a 2x2 matrix story. This is now a 4x4 matrix story, and I've also got this. One thing to notice is about, if you look at this, that there's something very, very funny going on to watch out with the when you look at this, you're tempted to say, aha, this is this guy is gamma. What physicists would like to write as, gamma mu ddx, or gamma mu ddx mu, is that this is a nice, and that this uses the Lorentz uses the Lorentz metric to raise and lower indices, and that this is a nice, and that you're writing some Lorentz invariant thing. But if that were true, if this really were a Lorentz invariant thing, like you would like to think that you're doing, and why you think you might want to put a minus sign here, is that you would find that that's a then this guy would be a Lorentz scalar. But the thing is, this is not. Remember, this is a first order differential operator. He's not a Lorentz scalar. We'll see how he transforms. So this guy is actually not. This guy transforms in. This guy is not invariant under Lorentz transformations. He actually transforms in a really interesting way under Lorentz transformations, which we'll get to in a minute. He actually transforms like a vector, and so really what you're doing is you've identified the space of the vector space of Minkowski space with a with these generators with a subspace of 4x4 complex matrices by using these generators. Okay, and so anyway, we'll get to this in a minute, and it might be a good idea to maybe it's better if I write this in momentum space. So in momentum space, then when I Fourier transform with respect to ddx0, I use the opposite sign to have so that the Fourier transform is a Lorentz invariant thing. There's an extra sign when I transform here, so this is going to be in momentum space. This is going to give you an I gamma. Let me say I gamma 0 p0 minus I gamma 1 p1 plus minus I gamma 2 p2. Anyway, so you've got so you do actually see a different sign here when you Fourier transform, and so but I'd say that the relative sign of these terms is kind of very confusing. In some sense, to make life even more confusing, you should realize that if you decide to change the sign of this, if you decided to make gamma 0 minus gamma 0, you would still, all you would be doing is you would be, that would not change this condition because the two minus signs would cancel. And so all you would be doing if you change the sign of gamma 0 and to change the relative, if you could change the relative sign of this guy and these guys just by doing by just going to a different set of matrices that satisfy the same conditions. So you're actually just changing your representation of your gamma matrices would also just change these relative signs. So these relative signs are not actually something physically meaningful, unlike in the what you would expect if the relative signs had to be there for Lorentz invariant. Okay. Anyway, let's go. Let's see. So let's now define. So this then now these relations are cooked up so that if you take if you square this thing, you're just going to get the Lorentz invariant version of the Laplacian. So let's just do it. Let's say that. So that's the this Dirac operator is it's square. If we square this operator, then we're going to get minus e squared dx0 squared. Then I guess I'll write this as pad squared. And sometimes we write this as box squared. So it's just the operator that this. Now we're back to the operator that we've been seeing in the Klein-Gordon story. It's just kind of the Lorentz invariant version of the Laplacian. Okay, and if you write this in terms of p's, you're going to get those i's are going to give you a minus sign, and then you're going to have a minus p0 squared plus p vector. So it's going to be p0 squared. So in the length of the space, this operator is just this. The square of this operator is just this. Okay, so then what you find is you can rewrite so you have you can use this to do this computation. So this is all you need if you want to talk about massless particles. But if you want to talk massive particles, what you need to do is to use this fact. If you quantize it, if you multiply these things, you'll the cross terms will cancel, and you'll pick up a minus m squared term here. So what you'll have is you'll have the box plus minus m squared. It's m squared. Okay. So the operator that you used to from the Klein-Gordon theory, for the massive operator, that actually kind of factorizes in this way. So the Lorentz invariant Laplacian is just a square, but if you put in a mass term, it factorizes in this way. And so now what you want to do is, so if you want to, so I guess I should say what the Dirac equation is. The Dirac equation is really just that you pick one of these, like d hash minus m psi x. So this is the Dirac equation. So it's and you can see that that if something satisfies the Dirac equation, so a solution to Dirac implies a solution to Klein-Gordon equation. So these things, because this is true, if you also hit it with this and get this operator is also going to be 0 on it. So what you've done is you if you can find solutions to this, it's a little bit like what happened in the Pauli-Schrödinger case. That if you could find solutions to sigma dot p psi is equal to 0, they would also be solutions of the anyway. They would also, you can also use them to get solutions of the Schrödinger equation. But you had anyway. But they gave you. Anyway, let me just say this. But the thing to notice is that these guys that note that so here, so psi x over C4. So if we're thinking about these guys being arbitrary being some 4x4 complex matrices, in general they're going to act on these on these 4-dimensional column vectors. So you should think of it as so they're going to be kind of functions that take values in C4. Except again, there's this quite interesting there are all sorts of interesting things happen then with reality conditions that I'll try to point out as we go along. Okay, and then in momentum space, you also have I p slash, and so this p slash notation was just that means that take the take the product of the p mu's times the gamma mu's. This is Feynman slash notation. So p slash is and again and there I'm using the as you saw there I'm actually using the different sign of the p zeros. But anyway, and so I a p. Okay. So what this is that so this becomes, it's a differential equation here, but again, we Fourier transform it, it becomes an algebraic equation. And so this for each p, this is just a 4x4 complex matrix, and you just have to find the you have to find the four-dimensional column vectors which satisfy this condition. Okay, and the I guess the other things to notice is that this is so the Klein-Gordon equation was second order. So if you wanted to specify a solution, you had to specify the values of psi and of the derivative, time derivative of psi at time is equal to 0. But this is a first order equation. So determine line. So if you know what psi of x vector is at time, if you know the solution at time t is equal to 0, you know it all at all later times. Okay.
So why am I thinking about the D-bar equation in complex analysis?
Well,
so are they somehow similar?
Well, there is actually there's a related story. Yeah, maybe I shouldn't say something about the So actually, maybe that is a good thing to mention. It is a good thing to mention that actually, if you ask, so I'm doing this in 4 dimensions. If you ask, what's the 2-dimensional version of this? Well, the two-dimensional version of it actually is very closely related to the Cauchy-Riemann equations. So if you try and ask, what's the Dirac operator in 2 real dimensions? So it's an operator on the plane. Square is going to be the Laplacian. Yeah. So then the standard. Anyway, yeah. You can work out what happens just in two dimensions, and you'll find that in 2 dimensions, the analog of all this is essentially that it's a simple transformation on the standard story about what solutions to the Cauchy-Riemann equation in the plane, and what it means for functions to be analytic in the plane, and the relationship to harmonic functions in the plane. So you can, I don't want to go through that, but in general, there's a much more you can morally think of this a little bit like what happened is that you really well, anyway, this is the beginning of a long and kind of fascinating story, but what really happens is that, remember, at some point I told you about differential, looking for solutions to Laplacian is equal to 0, but it wasn't just the not just on functions, but on differential forms. Okay, now if you think about differential forms and your manifold is actually a complex manifold, then your differential forms have they have kind of pieces which are, they have generators which are holomorphic and generators which are anti-holomorphic. They have not just dx's, they have dxi, they have dzi and dzi bars. So you can do the whole story of differential forms on a complex manifold, and then you end up with something. You end up looking at equations that are actually related to this, but there's an interesting difference. There's a kind of a they're twisted by an extra piece of structure which relates the two. So actually, what happens in higher dimensions and complex manifolds is you have a d, your d slash is closely related to d bar plus the d bar adjoint. So this is the analog of that Dirac d, but for complex things, and this is its adjoint, and then this guy is basically this guy, but you have to and then there's a difference. There's a twist you have to talk about. So I'm sorry, I can't really completely answer your question, but that's basically the story. Basically, the story is that in the plane, the Dirac equation and the Cauchy-Riemann equations are essentially the same thing. And in higher dimensions, you have to look at complex manifolds. You have to look at kind of complex differential forms, and you have to form this operator is related to the Dirac operator. So let me. Okay, but that's a much trickier story. So and you know, in general, the whole story of kind of Cauchy-Riemann equations and holomorphic functions, especially in higher dimensions, is a very tricky business. Okay, let's get back to something more sensible here. Try to finish this. Okay, so if I write this, okay, so let's to understand what's so this is our equation, or this, but let's write it in it's a first order equation, so let's write it like a Schrodinger equation. So so you have gamma 0 e dx 0 plus, let's call it gamma vector dot minus m psi that. 0. So, you know, but then you can write this in the form of a so this becomes I ddt. So x0 is just t psi of t x is so I, if you mess with this a little bit, you end up with this I gamma 0 and then a gamma vector dot vector minus m. So in some sense, so you have something like a Schrodinger equation where with on kind of 4 component, but now on 4 component wave functions with this operator is what I'll call the Dirac Hamiltonian operator. Okay, and then now if you Fourier transform this thing, well, okay, so Fourier transforming, you get minus gamma 0 gamma vector dot p vector plus im psi tilde of p is equal to e. So this is, sorry, there's a p. This is p vector. Yeah. Okay. Yeah. So this is going to be anyway. So it's going to. So what you're going to do is you're going to solve this thing using in Fourier space by going to by looking at the data at time 0, Fourier transforming it, make it as a function of p, and then looking at the at the energy eigenvalue equation, which is this. Okay, and then now if you but now if you square this, so this guy squared, and let me not work out this calculation, but anyway, this is if you squared this is gamma vector dot p vector squared plus m squared p vector. Okay, so what this means is that so this implies E is equal to plus or minus what I've been calling omega p vector So I think anyway, just try squaring this. I think I skipped a step or two. What you'll see, you quickly can get this and this, and then what you find is that the so you find in momentum space this condition is basically the square root of the condition that you know. So anyway, if this guy satisfies this, then that if you do it twice, you're going to get e squared, and e squared is going to be this guy. So you're going to get back the that's right. Plus or minus. So you're going to get back the standard kind of relationship between the standard relativistic energy and momentum relationship for mass m. But one thing to notice is that you definitely have unlike in the well, anyway, you definitely still have this problem. You still have this problem of negative energy solutions. So you've still got both positive and negative energy solutions. So people at first, I think actually supposedly the original motivation for Dirac to do this was that he was bothered that the Klein-Gordon equation had these negative energy solutions, and what about them? So he thought, well, I can, you know, if I do this, I'll get rid of them. But anyway, but this still had the you still have the negative energy solutions here. It's first order equation, but it's got anyway it's got perfectly decent negative energy solutions. Okay, so now let me just say, I'll stop soon, but let me just say a few things about this. Okay, so what are we going? How are we going to specify solutions? So solutions can be specified by one is just psi of x vector. Okay, I want to say. So these are four component. This is so four. Is equal to 0. So if you satisfy, yeah. Anyway, so if you if you start out with any kind of complex data here, then you're going to anyway, you're going to get a solution to the Dirac equation for all time, and that's and anyway, it's specified just in a one-to-one way by this. But now, if you Fourier transform it, let's see. Okay. So psi, if you Fourier transform it, now your problem is that for each p vector, you have two possibilities. You're going to have positive solution, energy solutions, and negative energy solutions. So you're going to have phi plus tilde of p vector plus psi tilde minus p vector. Okay. So you're going to have twice as much. You're going to have to. You're going to. Anyway, yeah. There are twice as many possible solutions because in some sense because here there was no notion of positive or negative energy, but here there is. Okay, and so now what you so we have to deal with this issue of these guys we're going to get back to the same problem that we had when we were doing Klein-Gordon theory, that you had to kind of quantize positive energy things and negative energy things in positive energy things with, if you like, with a create corresponding to creation of particles, negative energy things corresponding to annihilation of particles in order to get a kind of relativistically invariant picture of the world. But maybe what I want to do, so I'll start on this next time, but these are our basic spaces to work with, and so this is going to be our okay. So the possibilities that we're going to look at are going to be one thing to do is to impose a condition that it's going to turn out to be possible to take those gamma matrices to be real matrices, and so we're going to take psi of x vector to be real combination of these guys, and then what's going and if you do the Fourier transform, that just means that the negative energy thing is determined by the positive energy thing. That they have to be for this to be real. The conjugate of this guy has to be its value at minus p. So at minus p. So you have you end up relating these two guys. But this is called. But if you take these guys real, then what you've got is you've actually got so your phase space for each value of x is then 4-dimensional. So you've in some sense got you've got two kind of degrees of freedom, and this is going to correspond to real to real spinors. Well, let me talk about this. This corresponds to what I call the real. So this would be the same thing you got if you talked about quantizing two real scalar fields, and then it corresponds to spin. So spin, it's a spin 1/2 degree of freedom. Okay. So remember, so the point is that the phase space is 4-dimensional for each value of x, and so this would correspond to if you had two real scalar fields together with their corresponding momenta. That phase space would also be 4 real dimensional, and the two these 2 degrees of freedom get organized into a spin 1/2 degree of freedom. So that if you ask how rotations act on this, it's going to act in spin 1/2. And this is something that's called, I'll talk about next time. It's called a Majorana spinor field. Or what you can do is you can break up well, maybe I better not. So let me say this, that if m is equal to 0, you can write, and then d slash is going to be of the form you could put it in block diagonal form, something like this, and then what you can do is, and then you can separate this out, and then saying that this guy equals 0 corresponds to just this operator. I'll call this, I guess, d slash file, d slash file. And then you're going to have psi, I don't know, I forget how it goes, left or psi right. So you then divide. Anyway, this basically at n is equal to 0. These degrees of freedom decouple, and instead of having 4 complex degrees of freedom in general, at a point you can have you can just restrict and just look at 2 of them, and these are going to become Weyl. These are going to become Weyl spinor fields. And then the third one is that if you actually put these together, that putting these together, you have 2 for general for arbitrary m, you have Dirac spinor fields. Okay, and all of these things in some sense have spin 1/2. These are spin 1/2. These are kind of helicity 1/2 massless fields, is what you get this way. And this is and these are in some sense the same degrees of freedom as these guys, just organized differently. So here I'm just restricting to a C2, and so my fields are taking values in a C2 at each point. Here it was an R4, but so in some sense, Majorana field and a Weyl spinor field are the same number of degrees of freedom, except here you're thinking of it as a complex spin half degree of freedom. Here you're thinking of it as a real spin. Anyway, here you're thinking of it as a real massive spin half degree of freedom. Here you're thinking of it as a complex helicity plus 1/2 or helicity minus 1/2 degree of freedom. And here you're putting it together. Here anyway. So the Dirac spinor fields in some sense correspond to 2 Weyl spinor fields, or they correspond to what you would get if you took this theory and complexified it. Remember, and decided I'm not going to talk about real scalar fields. I'm going to talk about complex scalar fields. And I'm going to complexify things here. Then you would get to here. So anyway, so these are the different theories that you get. I think what I'll do next time is I'll try to go quickly through the general story of how to the specific things that happen when you quantize these things. But in some sense, all that's going to happen is that you're just going to look at the you're going to look at this information and pick out anyway, you're going to look at this information and then just use this to parameterize the spatial solutions of the Dirac equation, and then we're just going to for each p we're going to quantize that direction in the space of solutions, by the standard oscillator methods that we've used before, and that's all that we're going to do. But the technology you get into when you're doing this, it can get a little bit intricate. But I want to at least kind of give you the overall shape of the structure of what you're doing. When you actually start doing calculations, you'll see that you have to you typically have to make some choices, just like they're analogs of what you had to do in the theory of photons. You had to choose these polarization vectors to get you solutions. Here you're going to have some other analogs of polarization vectors you're going to have to choose here, which make the whole thing kind of a mess. And there's a lot of different choices you can make. But I'll try to keep straight the kind of general structure of the problem. Okay, I better stop now. So Are there any questions about this kind of beginning of spinor story? I'll try to, there'll be a lot more on Thursday. Okay. And again, and this is what the stuff that I'm doing here is typically, yeah, I mean, so some version of this is in pretty much every quantum field theory book. So there should not be a quantum field theory book that doesn't tell you about the Dirac equation and what its solutions look like, and what the different ways of parameterizing them and thinking about them are. So that's going to be pretty much in every book. I mean, a lot of the more modern ones, they'll do some kind of version of path-integral quantization. If you look back to what I'll be doing in more canonical quantization is you may have to go to some older books to find that in a more detailed way. Okay. Okay. Well, if there's nothing else, then let me stop for now. But please do. I'll be around for a while this evening. Please come back and say hello. Okay. Bye now.
Thank you.